Hello everyone, it's a pleasure to learn the content of this class with everyone. Before class, please recall this question. How do archaeologists speculate? We have already learned about it in our exponential function. After the death of an organism, the original carbon content in its body, it will decay according to a certain proportion, which we call the decay rate. After approximately 5,730 years, it will decay to half of its original value, and this time is called the half-life. According to the above changes, what is the relationship between the carbon-14 content in organisms and the number of years of death? We found it in learning exponential functions. When the number of biological deaths is x and the carbon-14 content of the deceased organism is y, we obtain an exponential function of y with respect to x. Y is equal to half of the 5,730th power as the base of the x power function. Of course, x is the number of death elements from 0 to infinity. The exponential function actually characterizes the problem of studying the law of exponential growth or decay, and this exponential function characterizes the law of the decay of carbon-14 content in organisms with the change of death time. When we determine the element x that causes the death of an organism, we can calculate its carbon-14 content y within the organism based on this exponential constant. Let me ask you a question: how to calculate the death element of a dead organism with carbon-14 content? Based on the relationship between exponents and logarithms, it is easy to obtain that x will be equal to the logarithm of y with the base at half the root of 5,730. When we give the content of carbon-14 in the birth object, we can calculate the corresponding biological death element x based on this logarithmic equation. We know this is an exponential function. Is this a function? That is to say, when our y is changing, we will correspondingly obtain the value of x. So, is x a function of y? To understand this question, we first need to recall what a function is. So what is the concept of a function? Let's reminisce together. Let A, B be two non-empty sets of real numbers. If any number in set A follows a certain correspondence rule, there will be a unique and definite value y corresponding to it in set B. So it is called a function from set A to set B. We remember that y equals fx, and of course x belongs to set A, which is our domain of definition. So, based on the concept of a function, let's reflect on our function where x equals. Is half of line 5,730 the logarithm of the base y a function? To determine if it is a function, we need to analyze the concept of our function. That is to say, this is an exponential function, and we can easily see that when x belongs to 0 to positive infinity, our y range is actually 0 to 1. So in other words, if I say to take any y between 0 and 1, can you be sure that the only x between 0 and positive infinity also corresponds? In other words, when y takes any value, can we uniquely determine which x corresponds to it? So according to the exponential function graph, we know that we can randomly take a number y0 between 0. Starting from y0, draw a straight line parallel to the x-axis, which will be the only intersection point with our exponential function. If the coordinates of this intersection point are x0, y0, then y0 will uniquely determine an x0. In other words, given any value of y between 0 and 1, I can always uniquely determine an x value corresponding to it from 0 to infinity. So obviously, we can also call it this function, which is a function from the set 0, 1 to the set 0 to positive infinity. So, since this is a function, what are the characteristics of this function? A function must have two variables. One is the independent variable and the other is the dependent variable. So, in this case, who is the independent variable of the function? We are studying the changes in the carbon-14 content y of an organism to determine its time of death x, so this independent variable is obviously y. And this variable should be our x. So, this function is different from the one we learned before. The function definition we previously learned that the independent variable is always x. Therefore, this does not contradict the concept of the function we have defined. In fact, without affecting the essence of the function, we can generally follow the principle that our independent variable is called x. If we take x as the independent variable and y as the variable for a typical function, then we can change y to x and x to y for this function. However, this does not affect the essence of the function. So for this function expression, I changed it to y equal to half of the root of 5,730, which is a multiple of the base x. So this is the new function we are going to learn today. This function obviously still has x as its independent variable, but it has undergone a change. Who is this independent variable? Actually, it's the name changed from y above, and this y is actually x above, which we also call y, a function of x. We call this function y, the logarithmic function of x. What general conclusions will you draw from reviewing the research process together? We will first redo this lesson. Starting from a special question, I also inquire that the function of the carbon content in the body changing with the time of death is an error function. But when I want to calculate its time of death based on the content of carbon-14, obviously we can calculate that x is equal to the logarithm of y, which is half of 1 of 5,730 roots, based on the logarithmic and exponential relationship. Obviously, the independent variable here has changed. Who are we changing the independent variables for? 1, which refers to the carbon-14 content of the unearthed cultural relics. Calculate the time of its excavation based on the changes in its content. Next, we need to study because we are accustomed to calling the problem of function self-variation x and the variable y, so changing the name will result in y being equal to the logarithm of the base x at the root of 5,730 times. We call this logarithm the logarithmic function we are going to learn today. But this question is ultimately a specific base number, 5,730 times, with a root of half to the power of 5,730, which is an exponential type. What is derived is a root type. What are the characteristics of these three numbers? Containing these three numbers is a fixed constant, which is given a specific value. If I generalize it to a constant a, we will arrive at a general conclusion. For any exponential function with a as the base, by swapping the exponent and logarithm, we can find that x is the logarithm of y with a as the base. Our independent variable this time is y, and the variable is x. In order to be related to our usual habits, we rename the independent variable x and the variable y, thus obtaining our expression, where y equals as the base and x calls this expression a as the base. The logarithm of x, we call the previous function the exponential function method, so this is y, which is the logarithmic function of x. We introduced the concept of logarithmic functions. The general function y is equal to x, where a is greater than 0 and not equal to 1, and is called a logarithmic function. Among them, x is the independent variable, and its locality is from 0 to positive infinity. Let's take a look at this concept together. First, let's focus on a problem. The definition of logarithmic function is the same as that of exponential function, both of which are formal definitions. That is to say, special attention should be paid to the characteristics of the function, which is based on a and the logarithm of x. To help everyone understand this matter more clearly, let's do a question to see. For example, give the following functions. What are the sequence numbers of all logarithmic functions among them? Okay, to answer this question, the first thing we need to do is to determine whether a function is logarithmic and what is the basis for the function. According to the concept of logarithmic functions, we know that y is equal to a x, which we call a logarithmic function. So, to determine whether a function is logarithmic, we must pay attention to 3 points. First, the coefficient before the logarithmic sign must be 1. The base of the logarithm is a normal number that is not equal to 1, which means that it is a normal number that is not equal to 1. Or rather, it is greater than 0 and not equal to 1. The true number of logarithms is x. There is only an independent variable x. So, based on these 3 questions, let's take a look at this question again. Which one do you think is correct? We look at number 1, and it's obvious that its score position is 3x minus 2, not just x. So this is clearly not. What about the second one? The coefficient before the logarithmic sign obviously has a 2, so of course it is not. What about the third one? The base of the logarithm, not a constant greater than 0 and not equal to 1, but a variable. So is the fourth one? Perhaps you have already noticed that through the understanding of the original logarithmic equation, we know that this symbol represents the commonly used logarithm with a base of 10. So this structure, we also call it the commonly used logarithmic function. Its base is 10, and if it is greater than 0, it is not equal to 1. The coefficient before the multiple symbol is a true number with a position of only x, so it is clearly correct. What about the fifth one? This base number is the root 3 minus 1. So obviously, root 3 minus 1 is a constant greater than 0 and not equal to 1. It's just an irrational number. So obviously, it is also a logarithmic function. What about the sixth one? After writing this function, its base still doesn't look like this, but we know it's a natural logarithm we've learned before, and its base is an irrational number e. It's a multiple of the base x of e. That's obviously also the logarithmic function we learned, so we can easily find out who the correct option is for this question. The answer is B. Let's revisit it again. We have given each other a concept, and we need to note that we already know its formal definition characteristics. So there are two more things to pay attention to. The first one is that the base a is greater than 0 and not equal to 1. We know that the entire logarithmic function is derived from an exponential function, and in the exponential function, as we mentioned in the previous section, a is greater than and not equal to 1. So the first value of the logarithmic function is still greater than 1 and not equal to 1. And we say that the definition of logarithmic function is from 0 to positive infinity, which means that the independent variable x must be guaranteed to be greater than 0. What is this based on? It's obvious that we passed. The true number of a logarithm is a positive number greater than 0. So obviously we require that x must be a positive number. By focusing on these three issues, you will understand what kind of function is called a logarithmic function. Let's take another look at example 2. Find the domain of the following function. Everyone observe these two functions. Based on the analysis just now, we know that it is clearly not the logarithmic function we have learned, but it is closely related to our logarithmic function. So, what is the basis for solving a function domain? What should be the steps for solving this problem? We know that the domain of a function refers to the range of values of the independent variable x. Therefore, the independent variable of the first function is x. The independent variable of the second function is the maximum x among 4 minus x. By solving for the range of x, we can determine the locality of the corresponding function. So according to the concept of exponential functions we just learned, when we discover that the true number of logarithms is required to be greater than O. If we make the truth greater than 0, we will obtain the corresponding inequality. I just need to solve the inequality. Isn't the solution set the range of x for this function? This also determines the locality of the function. Okay, based on this feature, let's do these two questions. According to the concept of logarithmic functions, in the first question, x must be greater than 0, so solving this inequality is easy to find as long as x is not equal. So in this way, we obtain the range of x for this function, which is a set of real numbers with non-zero locality. For the second question, we require that for x is greater than 0. By solving this inequality, we also obtain that x is less than 4, so the domain of this function is the set of real numbers less than 4. Let's take another look at the question. Assuming that the initial price of a certain place is 1, with an annual growth rate of 5%, and after y years, the price becomes x. How many years will the price of that place double? Fill out the table below and explain the changes in prices in the area based on the data in the table. Okay, let's answer the first question first. The initial price of a certain place increases at a rate of 5% per year, and after 10,000 years, the price obtained is x. Obviously, based on this characteristic, we can easily associate it. The pattern of growth changes is consistent with the exponential growth function we originally learned. After external communication, what should the price x be? X should be equal to 1 plus 5% to the power of y, which satisfies the growth and variation law of our exponential function. 1 plus 5% can be abbreviated as 1.05 to the power of y, so x is obviously an exponential function of y. Exponential growth. Of course, this y is infinitely clear to positive. So based on the relationship between exponent and logarithm, we can easily conclude that y is equal to the logarithm of x with a base of 1.05. If we subtract this x, it should be 1 to infinity, which means our prices are increasing from the final one. So this model is targeted towards the logarithmic function we are learning. So y is the logarithmic function of x. The logarithmic function model also characterizes the pattern of y changing with the variation of x. What does it mean when our prices double? Obviously, the price used to be 1, but when I flip it over, it should be 2, which means that it has changed from x equal to 1 to x equal to 2. When x is equal to 2, I substitute x into 2, and the corresponding price is the logarithm of 1.05 with a base of 2. We can use the calculator in our hand to calculate that it is approximately equal to 14. In other words, approximately equal to 14 years later, prices will double. The second question is, let's fill out this form. According to our previous research, the logarithmic function has a base x logarithm of 1.05. So x varies from 1 to positive infinity, which means that x takes 1, 2, 3, 4 to 10 respectively. With the calculator in hand, we can easily calculate its corresponding change in years. What kind of price change pattern can you get from observing the changes in these years? We can easily see that we have been using it for 14 years from 1 to 2. 2 to 3, we used it for 9 years. So similarly, we used 3 points until the end of 7 to 8. It took 2 years from 8 to 9, and 2 years from 9 to 10. It is obvious that as prices change, the number of years is also increasing accordingly, but the growth rate is clearly slowing down slowly. That is to say, according to the data in the table, it can be found that prices in the region increase with time, but the number of years required for each increase is gradually decreasing. This is different from our previous exponential function growth, where the logarithmic function growth gradually tends to moderate. Okay, let's take a look at exercise set A, which consists of 1, 2, 3, and 4, and set B, which consists of 2, 4, 8, and 16. If x belongs to A and y belongs to B, what is the future expression that can establish a functional relationship between set A and set B? Conversely, if x belongs to B and y belongs to A, what is the functional relationship that can be established from set B to set A using the following expression? So for the first question, we can find that based on the values of x and y, we can associate their growth rate, which can be said to be an exponential function suitable for the model. I see answer 1. By substituting the corresponding 1, 2, 3, and 4, I will obtain the corresponding 2, 4, 8, and 16, which obviously match the exponential function 1. Therefore, the first answer that satisfies the function relationship is answer 1. Secondly, if the independent variable x is taken from a b, then obviously it will also result in the corresponding elements of the set A. Who does he satisfy? You may have also noticed that it actually satisfies the characteristics of logarithmic functions. When we put the value of the logarithmic function into the test, we find that it does satisfy the condition that all elements b can correspond to them in A. So we have obtained the logarithm, and it is obvious that there is a difference in the growth of these two functions. Logarithmic functions, exponential functions, linear functions, and quadratic functions are the functions of fundamental numbers that we learn. Their growth varies, and different types of data growth require selecting appropriate functions to characterize their changing patterns. This will deepen our understanding of them in our future learning. So that's all for today's lesson. Goodbye.